Okay, welcome to, gosh, losing count. It's day 22. Been a few lectures since I've had the chance to teach, so happy to be back. As a reminder of where we are in terms of the semester or quarter calendar, we won't meet this Thursday because that is a holiday, Juneteenth. So we have Thursday off. Next week will be our last week. On Tuesday, we'll have a guest lecture from Jin Kwan. And then Thursday, the final, following the same format as the midterm. And any additional, oh, sorry, I wasn't here for the Wikipedia presentations. I'm working my way through the video recordings. Those that I've seen are great. And yeah, normally it's always a treat for me to be there to celebrate everybody's great work. Unfortunately, this time I had some international travel that was booked like a year out, so it just wasn't possible. Any administrative announcements?
One piece of reminder that the problem set 2 is supposed to do this Friday. We previously said it's Thursday, and we realized it's the federal holiday. So if you plan to hand it in a little earlier or a little later, Friday is the due date. And we preferentially would accept the paper copies this time, since most of y'all do it on paper. And if you did it on electronic, like, that's totally okay. Just send us the PDF. But yeah, we will mostly accept the paper version.
And we will be mindful of the fact that the final's coming up and return that promptly so you have time to review and ask any follow-up questions. Any administrative questions before we jump in? All right, let's go for it. All right, today's topic is one of the favorites for me because it gives me the chance to take a walk down memory lane from my postdoctoral days, Scripps lab. And this is olefin metathesis. We'll start by reflecting back on the metallocarbene lecture. And at that time, we had already laid the conceptual groundwork for olefin metathesis. And so if you think back to that, you'll remember that metallocarbenes can react with olefins in a 2+2 fashion. And if we think about this dichotomy that we had introduced at that time, or this continuum of Schrock type carbene, Fischer type carbene, that have different polarizations of the carbon metal bond, then those catalysts that have proven to be best for olefin metathesis tend to be somewhere in the middle. So there's not necessarily strong dipolar interactions or dipolar forces. And that makes sense if you think that the reaction that needs to take place is this 2+2 with a electronically neutral olefin. So we have our 2+2 to make a metallocyclobutane. And from this metallocyclobutane in the, you'll have to forgive me, I'm using my wife's iPad today. So there's all sorts of, I'm sure going to be all sorts of surprises. For a productive metathesis reaction, we have this very familiar sequence of 2+2, retro 2+2, and the overall effect is this so-called changing of the partners dance that takes place. But from this putative metallocyclobutane intermediate, there are other side reactions that could and do take place. And so we covered some of those in the metallocarbene lecture. So from looking at this intermediate, can anyone refresh my memory on what else could happen here? Amy?
You Product elimination.
reductive elimination, okay, and what would that form?
Cycle.
CC reductive elimination gives a cyclopropane, and what is the metallic byproduct?
Just the. Just I guess,
The naked metal.
yeah, naked metal, okay.
And if we're considering this, considering oxidation state, then because it's a reductive elimination, it would be reduced. So it's the naked metal in the N-2 oxidation state. So we have cyclopropane. See, this is what I mean. It's going to be full of surprises with my wife's iPad today. Let's see how this goes. Okay. Voila, okay. Cyclopropane and then metal, and that metal, just to clarify, we can describe this in N-2 oxidation state. Very good. And it just so happens that there's a periodic trend at play here, so that as you move right on the periodic table, this reductive elimination becomes more facile. We saw this example from Raoul's lecture where a putative palletocyclobutane is prone to generated from a different route, obviously the Pial route, that is prone to CC reductive elimination. So the secret to the ruthenium-based olefin metathesis catalyst is that you're not so far right on the periodic table so that they can actually undergo productive 2+2 in preference to reductive elimination. What else can happen here? Yeah.
Kind of beta hydride elimination.
I've drawn it suggestively with the beta hydride elimination here. So what happens in that case? Walk me through the products that you could expect there.
You have a alkene that can coordinate to the metal center,
Okay,
and then have a hydride onto the metal as well, and
Okay.
then maybe reductive eliminate.
beautiful. And so what would your product be? Your final end metallic product here?
Oh,
Oh, it's
and
like hidden
metal.
text
and then-
box that I try to try to like reveal. Okay, there we go. All right. So we said, let me see, I think I have a hidden box here. Okay, so this is what you said. Beta hydride elimination, and a normal beta hydride elimination gives us an olefin and a new metal hydride bond. In this case, we have this twist because we have a metallocyclobutane, so one of the carbon metal bonds remains intact. You thus generate a metal allele, and you gave us a hint of what would happen next, which is CH reductive elimination. And in this case, again, we're post-reductive elimination, so we have a N-2 oxidation state, provided that we're in at this stage. So these are some of the byproducts that are at play, and they really define the compatible metals, oxidation states, and ligand sets that are productive. You really need to thread a needle when you consider all these possible byproducts to have ligands, to have catalyst structures that can reliably and reproducibly favor 2+2, retro 2+2 sequences. Okay, let's now orient everybody on some of the general types of metathesis reactions. I recognize some of this, maybe all of this will be review for this audience, so we'll go through it quickly.
Sorry,
Yes,
zoom in general.
yes, where do you want me to zoom in?
Oh, no, just like in general. Oh, no, like when you go through the lecture.
So, okay, yeah, when I'm talking about things, zoom in to where I'm talking
Oh,
about,
yeah,
is that
yeah,
what you mean? Okay,
Yeah, generally.
I will try to do that. Yeah, I realize you're watching on the smaller screen now, so I'll try to be mindful of that. Okay, so we'll talk about different metathesis reaction types. The first we'll introduce is called SHOP, and you will probably never encounter this in your life as a small molecule maker. This is the Shell higher olefin process. Very relevant and important for industrial manufacturing of olefin containing commodity chemicals, but not something that you're going to do because it's typically done with heterogeneous catalysts. But the idea here is this is a cross metathesis reaction that redistributes olefin substituents. I won't say too much more about it other than you should know that it exists because it's an important societally relevant reaction. Some more familiar reaction types for your life as a small molecule maker would be ring closing metathesis. This is a process that really was first formalized by Greg Fu when he was a postdoc at Caltech with Grubbs. And this takes a acyclic, typically non-conjugated diene, and then snaps it shut. Of course, all olefin metathesis reactions, as we'll see in this class, are in principle reversible. And so in order to drive it towards a particular product outcome, you need to introduce some kind of thermodynamic driving force. In the case of ring closing metathesis, that is most commonly release of gaseous ethylene. And so some of the tricks that folks will use to promote productive RCM as well as productive cross would be to sparge the reaction. So you're constantly removing gaseous ethylene as it accumulates. You can run reactions under what's so-called static vacuum, where you have reduced pressure in a sealed reaction setup. You can have solid phase scavengers of ethylene. But in any case, if you want the reaction to push forward, you need to remove ethylene. We have a process called ROMP, ring opening metathesis polymerization, where typically some kind of strained cycloalkene starting material will be used. So think here things like norbornene, cyclooctene, cyclooctadiene. We'll talk in a moment about strain energies of different ring sizes, but here the thermodynamic driving force is release of ring strain, and depending on the nature of the monomer, you have varying levels of backbiting or chain transfer or processes that are relevant if you're a polymer chemist, but as a small molecule chemist are less important to you. And olefin metathesis has this important feature of being what's it called a living polymerization. Living polymerization is a specific term in polymer science, but really we don't need to make it so complicated. It's exactly what it sounds like. You have a growing polymer chain where you have your intact catalyst at the end of the polymer chain, and so it is alive in a sense. What are the consequences of this? This means that you can use living polymerizations for production of things like block copolymers, where you can use a particular monomer. So let's say you use norbornadiene, you run the reaction to exhaustion. The propagating polymer chains still have the catalyst at the end, so you can charge with another monomer. Now let's say it's cyclooctadiene, and then it will be off to the races again until it consumes all of that monomer. And that's a way of making these predictable block copolymer structures. ADMET is another less common form of polymerization. ADMET stands for acyclic diene metathesis. And it's effectively somewhere in between ROMP and cross metathesis. So you have acyclic diene starting material, and then depending on the concentration you run, as you can appreciate this, there can be competitive ring closing reactions here since starting materials could be the same, but depending on the concentration and operating conditions that you run at, you can actually favor oligomerization or ultimately polymerization. And then cross metathesis, this is one of the most, I think this and RCM are probably the two most common types that you'll encounter as synthetic organic chemist. Some of you will have already run these reactions. So cross metathesis just refers to the coupling. You can view it as a cross coupling effectively. It's two distinct olefin starting materials. I've drawn here the relatively simplified version of them both being terminally substituted so that we generate ethylene as a byproduct. And we'll talk about the selectivity rules for mixing and matching to get selectivity above statistical control. And then E9 metathesis and ring closing E9 metathesis are powerful tools for synthesis of diene starting materials. When I was learning this myself as a student, I always struggled with figuring out what these reactions actually make. And I use this mnemonic myself to this day, where to figure out an E9 metathesis product, you take the ene component, you split it in half. Here I've shown it in blue circle, red circle, and then you just stitch it to the two alkynyl carbon atoms. And you can do that in fully intermolecular sense or in an intramolecular sense, and it still gives you a way to predict the products that you form. So with ring opening metathesis polymerization, a really important, sorry, I have a bug on my screen. Really important consideration is release of ring strain. And first pass approximation, the more strained, the better monomer the starting materials are. And so just, again, this high level analysis of ring strain allows you to predict, rationalize, and then ultimately predict what types of cycloalkene monomers in general are going to be good for ROMP. So for example, would you expect a cyclohexene to be a good ROMP monomer? No. Would you expect cyclopentene to be a good monomer? So you not really sure. What about cyclooctene or cyclooctadiene? Looking better. What about norbornene? That looks like it's going to be quite reactive. So first pass approximation, ring strain is a good guideline for what monomers will ROMP. But it's also interesting to look at some of the boundary conditions. So let's consider the most possible strain system that you can imagine, a cyclopropene. These have a huge amount of potential energy. And so they look like they'd be great ROMP monomers, but not so fast. So what actually happens here? This is work from Yan Xie. Yan's a professor at Stanford, formerly a graduate student with Bob, and has done a lot of interesting metathesis work with cyclopropenes. So here we go. We're going to take this third generation initiator, and we'll talk about the nomenclature used here, but it's a third generation Grubbs catalyst, react with this specific cyclopropene. You can imagine to yourself how you make this based on the structure, perhaps some carbene insertion into an acetylene equivalent. In any case, this is the initial adduct shown, and I guess I'll draw this in brackets. So here's the initial adduct, 2 + 2, retro 2 + 2. But what happens next? I can tell you that this reaction happens very rapidly, but only happens once. And so for a ROMP reaction to happen, of course, it needs to happen rapidly and needs to happen repeatedly. So why would this only happen once when there's so much strain energy? Thermodynamics are definitely on your side. So what must be the problem, Al?
I think similar to some substrates in the lab, if you have that alpha geminal center, it might be difficult to do olefin metathesis.
Why?
Sterics.
Steric clashing. A story as old as time. So after the initial alkylidine transfer or benzylidine to alkylidine transfer, you have this new adduct, but let's take, if we take a deep look at it, look at this. We have a fully substituted allylic position here, quite hindered, and then the starting material itself is no slouch when it comes to steric hindrance. It's going to experience quite a bit of steric clashing when it's trying to approach the ruthenium center. So sterics prevent this reaction from this putative polymerization from proliferating or propagating. So hypothetically, what could we do here if we wanted to convince this to perform a polymerization? Sebastian, you've got an idea?
I don't really know if this is a good solution, but I guess I'm curious if you can coax your carbanoid to do a second polymerization with a different monomer.
Aha.
Alternate.
Beautiful. I like it. So if you had that idea 10 years ago, then you could publish it in JAX as Jan's group did. So that's exactly the trick that they played. It doesn't like to go successive metathesis with itself, but it would be happy to, at this point, find another monomer. And then you can achieve this unique form of alternating polymerization where the cyclopropene is hot and selectively reacting as long as it's not reacting with a propagating ruthenium alkylidine with this bulky center. And so this provides a means of achieving alternating polymerization. So it just goes to, I sometimes say in my group, you know, a lot of the best researchers who sustain success over long periods of time, every time they run an experiment, they never lose. They either win or they learn. You either win, you get the outcome that you want, or you learn and you, if you can truly understand why it didn't work, you can normally do something else that's just as interesting or sometimes even more interesting. So in the context of organometallic catalysis, if you make a catalyst and it's not reactive and is really sluggish, maybe that means that the intermediates are super stable, and then that can give you insight into the mechanism that you can't obtain with the really hot, spicy catalysts. Okay, let's take a walk down. I mean, I think everybody knows at this point in the class that I'm always a sucker for organometallic history, and I'll try to go through this quickly because I know it's not everybody's cup of tea, but we'll just talk about some early examples. Where did the genesis of this field come from? Because it was really lying in wait for quite a long period of time in the 60s. Grubbs initiated his career in the 70s, and a lot of these observations were out there, but there was not necessarily groups working on it in a dedicated way as came to pass in the 70s and 80s. So there were sporadic examples throughout the 60s. Here's one from DuPont, early report 1960s. What they were thinking might happen is that they treated norbornene under these Ziegler type conditions. We talked about Ziegler polymerization. It's a coordination polymerization for making polyolefins. Typically, if you imagined a Ziegler polymerization of norbornene, you'd have a product that would be fully saturated. But when they run this reaction, actually, they find out that the product contains CC double bonds. And so that's a sign that there's something else going on. It's not this traditional coordination mechanism. And there's evidence that the norbornene ring has opened. In parallel, but in a different world, in the world of olefin refining, Phillips Petroleum had observed that with a heterogeneous catalyst, they could take propene as an input. And if, given what we know now, what would you expect the distribution of products to be here? You go in with C3, your products are going to be what? Is it going to be all possible carbon count? No. Alex says no. So what is it going to be, Alex?
C2 and C4.
C2 and C4. Beautiful. Not that complicated here. They see that, again, if you imagine some other type of reaction, some polymerization, oligomerization, et cetera, you could get to different carbon counts here, but you see this very defined ratio of only remaining C3 starting material, and you're forming cleanly C4 and C2. They called this at the time olefin disproportionation. And likewise, in the 60s, early example of cyclopentene. We said cyclopentene is not a great monomer, but you can polymerize it under some conditions. Here's an example of homopolymerization of cyclopentene with stereo control based on the identity of the metal it's employed. And so you see an interesting combination of researchers in the petrochemical industry, researchers working, NADA, you'll recognize that name from Ziegler-Natta polymerization fame, researchers coming at it from the angle of polymerization, and then Calderon, who has an interesting life story. He, if I remember this correctly, is a former Israeli paratrooper who then was really the first person and probably an unsung hero in the area of metathesis to make this connection that the same catalytic systems that were giving rise to this olefin disproportionation could also promote this unusual type of polymerization. And he made that observation in the context of ring opening polymerization of cyclooctene, as well as this redistribution of olefin substituents around alkene containing hydrocarbon feedstocks. And so at equilibrium, what is the statistical ratio that's reached here? C4, C5, C6. Very quickly, what do you think? Yeah.
Not very sure about their energy difference, but if they are equally stable.
Yeah, let's assume they're equally stable. I think that's a fair
1 to 1 to 1.
1 to 1 to 1. Any takers or disagreeers for that? And the way to think about that was just that for every C4 you make, you need 2 C5s effectively, right? So this is not a reflection of their relative stabilities. It's a reflection of the connectivities, if that makes sense. Okay, there's some very fascinating and at the time very controversial mechanistic debate. I would direct the interested student to this CNE News article. This was if you remember, the timing here is quite interesting. This is pre-Nobel Prize, and so the CNE News article was trying to kind of get the record straight for who did what and when and how it influenced who else did what. But from these observations alone, if we think about, we put ourselves in the mindset of those chemists working in the 60s, it's not really obvious how these transformations would be taking place. And one of the aspects that muddies the water, so to speak, is that, remember our timelines, the understanding of carbines as a legitimate organometallic entity and actually a prevalent organometallic entity. This didn't happen until the 70s. And so the notion that you would invoke such a species as an intermediate in the catalytic cycle was pretty far-fetched. And so at the time, and from the studies I showed you before, so I've simplified, rather than draw R1, R2, R3, R4, I've just simplified this and color-coded it, like very simple situation, deuterated, non-deuterated. From this type of analysis, the community had an appreciation that at some point this double bond needed to be cleaved, but there are many different ways that you could draw this. And so you don't observe any of the putative crossover products that would implicate that deuterated, like the deuterated CD and deuterated CD3 bonds are to the alkene are being broken. You know that they're staying intact, and you know that there's some mechanism needs to take place to break this CC double bond. And so there are a lot of mechanisms, and several mechanistic hypotheses put forward. All of them in the year 2025 make our hair stand on edge a little bit and make us uncomfortable because they're pretty bizarre by today's standards. But again, put yourself in the shoes of folks in the 1960s. The organometallic chemistry is seemingly full of bizarre stuff, like the discovery of ferrocene, stable aromatic structures that seem to violate understanding of our prevailing understanding of organic chemistry. So here's a proposal from Calderon. A lot of these are ill-defined. It's hard to totally understand what they mean here, but Calderon's proposal, it doesn't, in some ways, it doesn't look that far off, but you have this strange step where both olefins coordinate. They form some kind of ill-defined cyclobutadiene bound metal, and then you have successive bond breaking until the partners swap and they can dissociate then in metathesized form. Lawandos and Pettit had a similar kind of idea. This one also should make you feel a little bit uncomfortable. Spontaneous dissociation of the olefins to their constituent carbene parts, and then presumably controlled by their stereochemical orientation. They combine in one particular way to give the so-called cross product. Grubbs, of course, was working actively in metathesis through the 70s, and an interesting historical note is that he didn't have the mechanism right himself, but I think his mechanism in his defense at least looks like organometallic mechanisms that were known at the time. And so there's nothing that really makes you uncomfortable about this, save maybe one step. So the idea here that Bob had was, or Bob's group had, was effectively an oxidative cyclometallation, which again, we've seen before in class. So you go from an oxidation state of some low valent oxidation state of the metal. So for example, palladium 0, and then you have an oxidative cyclometallation, so palladium 2 hypothetically, or ruthenium 0, ruthenium 2. And then you have some kind of shift, and this is the part that's probably not well defined. You have a metallic shift that involves some kind of CC cleavage event, and then the reverse, microscopic reverse of which just took place. Now, instead of the oxidative cyclometallation, you have the reductive fragmentation, and then out would pop your product. The individual who got the mechanism right was none other than Chauvin. Of course, we know him now as a Nobel laureate in his own right. Chauvin published his work in 1971 in a little red polymer journal that also I think was in French. But he was the first to articulate the relevance or the possibility of a propagating metallocarbene as the catalyst. And then now the steps look much more familiar: 2+2, retro 2+2 through a metallocyclobutane intermediate. And the key insight, and what really then guided catalyst development for the decades to come, was that the active form of the catalyst is a metal carbene. Again, this was somewhat of a foreign concept in the 1970s because the whole landscape of metallocarbenes was basically limited to those that had been published by the Fisher Laboratory. Even Schrock's initial Schrock type carbene had not yet come online at that point, or was that work was going on in parallel. There's some debate in the literature about the extent to which this proposal actually influenced what was going on in the field, given that it was published in a venue that was not widely read. And there's also some debate about who was the first, from a mechanistic perspective, from physical organic perspective, to unambiguously show through a strong inference, rule out all other mechanisms to show that this one is the most likely. And you can direct you to the work of Chuck Casey and Tom Katz here cited in these two Jack's papers. We don't need to get into a lot of old historical controversy, but these are the things that people were concerned about as it came clear that this work would get a Nobel Prize. This was the types of things people were concerned about. Who did what first, and how influential was it actually? So here was the problem coming that Chauvin did not really himself reconcile, is that he proposed a metal carbene, but the known metal carbines in the 1970s, the Fisher type carbines and Schrock's initial Schrock type carbine, which is the one shown here, this tantalum alkylidine that you should be familiar with, these did not do metathesis. It took a few years. Eventually, Schrock found a tantalum based complex that was metathesis active. It's not a good metathesis catalyst by any means, but it was metathesis active, providing some support to Chauvin's hypothesis. And then shortly thereafter, Schrock pivoted to tungsten, molybdenum, the metals that we're familiar with now, and then built out the necessary requisite ligand sets, such that these catalysts are now the most active known metathesis catalysts achieved regularly, achieving tens of thousands or hundreds of thousands of turnovers. The Grubbs catalyst chronology is an interesting one because it's interesting to me as somebody who knows quite a bit about Bob's career arc. He started in the early days, and we've covered some of these examples in class, with interest in titanium. So it's known that titanium alkylidines can undergo these 2+2, retro 2+2. And that was the main focus. It was really in the 90s that he made this strong pivot. So almost 15, 20 years later, made this strong pivot to ruthenium and eventually built out the toolkit that we all benefit from today. So why did they make that pivot? And there's an interesting story tucked in here that I think is not really well documented in the literature, but I'll share it with you today, which is in the late 80s, Grubbs had always had this interest that spanned organometallics to practical organic synthesis to materials science. And as part of his interest in the material science realm, the group was trying to develop these very bizarre and futuristic, when you think this is happening in the 80s, helical ionophore polymers. And the idea was that you could take an oxynorbornene derivative and perform, it wasn't called ROMP then, but some ring opening polymerization and get, if you built a 3D model, it would look like it would lend itself to being helical, and then you'd have all of the oxygen atoms from the oxynorbornadiene pointed towards the middle, and that could potentially be a means of ion conduction. A really provocative idea. What was the problem? All the known metathesis catalysts, let's look, are all early transition metal based. So they do not tolerate oxygen-based substituents. Well, they're far too oxyphilic. So they'd much prefer to pull oxygen out of an oxynorbornadiene monomer than they would polymerize it. They found this report of an ill-defined ruthenium system. So you go in with ruthenium trichloride hydrate, no ligand, but there was some evidence that this could promote ring opening metathesis polymerization in water. So they thought if it can work in water, there's a good chance it has high levels of tolerance for Lewis basic functional groups. They ran the experiment with the actual monomer and found that even though this was ill-defined, you could eventually get a propagating catalyst that could polymerize these oxynorbornadiene monomers. What was the problem? It's the same problem then that was facing these other metals. If this is truly a metathesis reaction, then a well-defined ruthenium carbene should also be metathesis active in the right ligand environment. And so you see there's a 3 or 4 year induction period from that point. Eventually, the first metathesis active, well-defined ruthenium carbene was synthesized by the Grubbs group in the early 1990s. It's the one shown here. I think you can think of this as it's the 0th generation. It doesn't get a generation number. It's the OG version of a Grubbs catalyst. It has this interesting vinyl carbene structure that we don't see in the metathesis catalysts today. So maybe I can first pose the question of synthetically, how would you make something like this? If you put yourself in the shoes of a student or postdoc in the time, and this particular contribution came from Sanbin Win, who some of you might know now is a professor at Northwestern working at the Organic Chemistry Materials Interface. So Sanbin, you put yourself in Sanbin's shoes and Grubbs asked you, go make a ruthenium carbene, how would you do it? Pierre, you have an idea?
Can you have ruthenium add into a geminal dihalo species and then with lithium form the carbene?
Geminal dihalo species. I like that idea. So you're a gem dihalo alkane. Is that what you have in mind?
Yeah, the allylic position.
At the allylic position.
We're talking about the first complex drawn at the top left.
Yes.
So if you have a dihalo.
Ah, I see. Okay, I see. Okay. Yeah. This is kind of like analogous to some of your idea is somewhat analogous to like the recent work of like Chris Ueda's group, who does a lot of these vinylidene transfers from dihalo species. So I like that proposal. You'll see it's not one that I have sketched out here, but the idea, if I understand you correctly, is to have and then this carbon, and then you have XX, is this right?
Yeah.
I think that's logically sound in terms of oxidation state. Yeah, Sebastian, what do you think?
Yes, this would be in the same oxidation state, but could you make the like Schrock carbene, like the methylene carbene, and then take enal and see if you can just do it?
The Schrock type.
Actually, no, you'd be off by. I'm basically trying to see if you can go through like olefination chemistry and then like trap out an intermediate.
Okay.
But I think your oxidation state would actually be wrong. So probably not that.
So I think we can build on Pierre's proposal here and just kind of like get to this same, what I'm going to do is use the same logic, but just get to a stable symmetric intermediate. And it's something that's a little bit familiar here, which is the cyclopropene. So it's the same number of atoms in the same oxidation state as Pierre has. And then we rely on presumably some formal CC insertion process rearrangement. But that works, but that's not the way that these catalysts are made today, since obviously it'd be annoying to have to make cyclopropene every time that you want to make a metathesis catalyst. So what's another way we talked about making metal carbenes in class previously?
The diazo.
Diazo, beautiful. Alex has got it. So we can also alternatively, and this is how these are made. Actually on frighteningly large scale, this is how these catalysts are made today from diazos. So not so much these vinyl carbenes, I think, kind of fell out of fashion. It's just if you don't want that group there if you don't need it. But let's say the more familiar benzylidene structure, you can see that conveniently disconnects to a diazo species. There are other ways too. You can make these from propargylic, suitably substitute propargylic alcohols, but this is a tried and true way made on very large scale. And so initial key discovery by Sanbin, the generation 0 catalysts, and then we're off to the races here. Once you have this key structure, ruthenium, carbene, and then you have a lot of room to play. You've got the X-type ligands to tune, you've got the L-type ligands to tune. This cyclohexyl, this tricyclohexyl phosphine version was developed and named the Grubbs first generation catalyst. Hoveda then in the mid 1990s made an important contribution that with a suitably substituted benzylidene group. The important point here is that you have some heteroatom at the ortho position. You can get a chelating structure, and this becomes especially important when combined with another development that I'll talk about in a moment, the advent of these heterocyclic carbene ligands, because it gives a fully phosphine-free structure. And phosphines lead to some deactivation mechanisms in metathesis catalysts. So the Hoveda version is now, so this is the first generation Grubbs catalyst. We have the first generation Hoveda Grubbs catalyst. There's this work, I'll share this as one of the readings for the class. I think it's really interesting, Hoveda's initial report on this, because it actually came from, he did not set out to get involved in olefin metathesis. It came from the context of applying olefin metathesis, this emerging olefin metathesis methodology in the context of natural products total synthesis, and found that the desired metathesis reaction would not take place, and instead you'd get this weird green-brown complex that seemed very, very stable and was able to pull out this chelated structure from the building blocks that he was using for metathesis, and then took that and ran with it, and of course has made an amazing career for himself in the area of olefin metathesis, among other contributions. But it really came from the willingness to take a detour from a natural product synthesis and figure out from an organometallic perspective what's going on, why isn't this coupling partner working well, what's this weird byproduct that's being formed, why is it so stable, et cetera. So the next key development came in the late 1990s and early 2000s, and that was the advent of N-heterocyclic carbenes. This is important in the broader trajectory of organometallic catalysis, because this was the first really convincing, compelling use case for N-heterocyclic carbenes as ligands that could do things that phosphine ligands couldn't. So we talked about the discovery of the first Arduengo type stable carbene, and you see that that's found here as well. And so contributions from many labs, Furstner, Wolfgang Hermann, Nolan, Grubbs, they were putting these on different metals and putting them through their paces in catalysis. And so it made sense to put them onto metathesis catalyst and see what happens. The results were not that compelling with this unsaturated backbone, and the key subtle tweak was to go to the saturated backbone version, this so-called Simez ligated. This was actually first synthesized by an undergrad in the Grubbs group. So I think if you as an undergrad synthesize a Grubbs second generation catalyst, it sets a pretty high bar for the rest of your career, but that's what happened here. And this was by Shen Ding, who was a Caltech undergrad and then went on to do work with Pete Schultz. He was a colleague here at Scripps for a while, working in the area of stem cell biology. So this then, the saturated backbone one was the winner. The role of the NHCs we'll talk about when we talk about the mechanism here, but the Cliff Notes version of it is that after dissociation of the outgoing phosphine ligand, you have a choice, a chemoselectivity choice that can either rebind phosphine or bind olefin. And the NHC ligand improves the selectivity for binding olefin, something to the tune of 4 or 5 orders of magnitude. So this version is the Grubbs second generation catalyst, and then in the polymer chemistry, this bispyridine ligated version is popular. That's called G3. And then in the more recent literature, we have catalysts that we will talk about in a moment that allow for control of stereochemistry in cross metathesis or macrocyclic RCM. So this version here from the Grubbs lab, a Z selective catalyst. You can just call it, it doesn't really have a name, just call it Grubbs Z. And we'll talk about how to make this and then the mechanism of the means by which it controls selectivity in a moment. So let me just perseverate for a brief minute on this third generation catalyst system, because this would probably be the one you're least familiar with as folks working in small molecule synthesis, but this is the go-to catalyst in polymer chemistry. So let's take an example of this from our chemist of the day, who I don't know if anybody would recognize. I'll give it a second.
Darren Fog.
There you go. Leave it to the Canadian to come through in the clutch. Darren Fogg. You want to provide any more?
She's from my under Ottawa.
Ottawa. And among Fogg Group's numerous contributions are in-depth studies of activation and deactivation mechanisms of ruthenium-based catalysts, ruthenium-based Olefin Metathesis catalysts. So most recently, it's been applications, just for example, applications of water-based or water-soluble Olefin Metathesis catalysts for things like bioconjugation, CAC ligated metathesis catalysts for feedstock conversion, and so on. So here's just an early example from the Fogg Group to illustrate this point about why the G3 catalyst is useful in the context in which it's useful. So we see here in this JAC study benchmarking G1, G2, G3. The G1 catalyst is not very good. The G2 catalyst is much better, and the G3 catalyst is the best. And I think this point, why this catalyst performs well, will be clear when we talk about the mechanism. The product here is just the standard norbornene polymerization product. The G3 catalyst is fast initiating because it's got these relatively weakly coordinating pyridine ligands. At least they're weakly coordinating with a late-ish transition metal in ruthenium. It's a hard-soft mismatch, and so they will fall off and allow the olefins, the polymers to the monomers in this polymerization to associate. So this gives fast initiation, lower reaction times. I think to orient everybody, the G3 catalyst in this particular series of reactions reaches completion to the tune of 2 hours, the G2 catalyst maybe 5 hours, and the G1 catalyst a couple days. So several orders of magnitude different. Okay, let's talk about synthesizing some of these catalysts, and we will do that by looking at the more modern, the newest ones, which is the Grubbs Z and the Hoveda, which I realize I didn't draw here. So I will draw that and give you a chance to take a minute and think about how you would make these complexes from any of the other complexes that we've covered so far today. All right, so take a moment and think about that. All right, let's do the bottom one first, because I think it's the most straightforward, this Hoveda one. So walk me through this. How are you going to make this catalyst?
The dihalo precursor with a silver salt if you're dithylate.
Sebastian's got it. And what might be the problem though if you tried a silver dithiolate salt that you could anticipate? Would you say the silver thiol interaction is going to be strong or weak?
I feel like it's a hard soft pairing, it would be quite strong.
That would be strong. So we know gold thiol interactions are super strong. Silver is in that same ballpark. So maybe that's not the one you would try first. potentially. So what would be like but this general idea is spot on. So you're saying basically something metal here, something metal here. Any other simpler metals that you would maybe try first before silver?
Magnesium. maybe.
Magnesium, great, okay. And anything else I think would be probably reasonable to try. I think in the actual reaction, they find that it's convenient to use a divalent metal starting material. You propose magnesium, which I think makes sense. They use zinc. And that works well. And then what if you just in the interest of completeness use, I told you, well, I want you to make this too. How would you do that? Make the Grubbs Hoveda second generation catalyst.
I couldn't get that from the cyclopropane, could I? No.
But you
the
can,
diazo- do diazo stuff.
you can make it from any other, you don't need to make the carbene. You can make it from anything else I've shown you already.
Then I'd probably want to make it from a triphosphate.
Okay,
So I'd probably take it back to the vanillidine to tricyclohexaphosphate ligands.
okay, so that's great. So you're gonna first make this from Hoveda Grubbs second generation, Hoveda Grubbs first generation and Simez free ligand. Beautiful, and that ligand exchange will work well, and then because they're Grubbs catalysts and super stable, column them. And if you wanted to make this, you can take this really all the way back, which isn't beyond the call of duty here, then you could do that by going from the Grubbs first gen catalyst. I've done some of these types of experiments myself. Plus the chelating benzylidine precursor. Very good, okay. This is a useful exercise because it will give a hint about how we're gonna make this top one, which I think the first thing I'm gonna do is shrink this so it's not so giant. Okay, so any thoughts on this one?
So we could probably do a similar thing using this time silver nitrate.
Okay.
Then you have to figure out how to make the alcohol.
Okay, this I like, so you got, that's a good call for sure. And then that means if I understand this connection, you're gonna put a halo here.
Yes.
So let's put. And you said silver, nitrate, sorry, NO3. Okay, and then you've got halide there. So that's a good first step.
Maybe to make that. You could see if you were to take back on your carbene, if you were to take it back to a beta halo adamantal or something,
Okay,
maybe you can do just oxidative addition into that bond.
okay, that's totally reasonable. So we recognize that looks like something that could arise from oxidative addition. Then we're gonna do beta halo adamantal group. What would be the problem with that?
Maybe the geometry required to do your oxidative addition is not really.
I think in terms of synthetic accessibility, you're gonna have a problem because you're either gonna need to bring that beta iodo adamantane through several steps, or you need to introduce it late stage. But then you're gonna have a site selectivity issue. So you're gonna do a radical CH iodination, but it's gonna prefer to go to tertiary position probably.
So then could you make the adamantal enamine instead, and then do something funny with Engle.
Adamantal enamine, but that would be, I think you would get a Texas carbon in that case.
No, you might be right about that.
What do you think there, Al, for this one?
Can you do some kind of decarboxylation from the acid, the adamantane?
Decarboxylation, what ideally, just tell me from, don't think about how you're gonna do it, but if I could tell you, you could put anything there in the precursor, what would you put there? For, to simplify everything, make it symmetrical, etc.
I was also thinking of the halide, but
Halide, okay, but not halide. What actually makes this symmetric? Well, as drawn, that doesn't look too bad, does it? So what if we're just gonna make that bond by
the CH.
CH activation? And then what is your typical base you need for a concerted metallation deprotonation flavor CH activation? You're going to have some kind of carboxylate base. So let's say it's pivalate, for example. So I'm gonna take this back a couple steps here. So we're going to have this here, whoops. Here, and this will be O-piv. And then we're gonna take this back to running out of space. So I'll try to. And then this pre-catalyst, this complex, you were gonna make the exact same way that we did the other one, which is to go from the Poveda Grubbs first generation and then bring in the free carbene. Okay, so then let's run this forward. So now we have Poveda Grubbs 1, we exchange the phosphine for carbene. We're gonna treat that with sodium pivalate. Or maybe we might need to go stronger, we might hit it with silver pivalate. We don't know. That is going to metathesize off the halide salts, install 2 PIVs, and then look at how these are geometrically disposed. We've got a PIV right next to a tempting looking CH bond. It will undergo CMD. But now we need to get from the PIV to the nitrate. So we have to do a few kind of like a concession step back to step forward. So we swap off the PIV for a halide, swap on the nitrate via silver mediated salt metathesis. Here.
Why do you need to, first of all, how do you swap the PIV to the iodide, and why can't you use nitric acid to go directly to what you want?
Well, what might you expect to happen if you treated this adduct, which I think is the one you're talking about, with nitric acid? What happens to carbon metal bonds in the presence of strong acid?
Yeah, I guess you protodemetallate.
You can do this actually just with sodium iodide. And the driving force is that you form a very strong soft interaction between ruthenium and the iodide. So it's a little bit of a trick. Like you could not under thermodynamic control, you could not easily go from pivalate to nitrate. So the trick you do is you go thermodynamically downhill to the iodide. And then you take advantage of the insolubility of one of the byproducts, in this case, silver iodide, to Lachapselier it over to the final product. So it's kind of like you do something that's close to either thermodynamically uphill or close to thermodynamically downhill by taking an alternative path. Good, questions on that? See, organometallic retrosynthesis can be fun too, right? That I love this complex, this complex A. It's just such a bizarre complex. If you really step back and think about it, it's got a metal carbon sigma bond, single bond, a metal carbon double bond. Somehow that does not undergo 1,1 migratory insertion, which itself is shocking. And somehow it can engage in this sequence of 2+2, retro 2+2 without deactivation. It's like absolutely shocking that something that looks like that could actually be a stable catalyst, and that all the evidence they have that exists in the literature is that it stays intact like that as it propagates. So what is the secret to the Z selectivity? So these two complexes, I won't go into this, but we'll provide references as backup reading if you want. These two complexes are a little bit different. So the complex B, they're both Z selective. If you take terminal olefin A plus terminal olefin B, react them in a cross, they will both give you Z product. And complex A is more Z selective. Complex B has this interesting property that it's actually what's called stereo retentive. This means if you do a cross that's not terminal-terminal, but let's say it's internal-terminal, and that internal is Z configured, it stays Z. If it's E configured, it stays E. And that's a feature that is not true of so anyway, if you have questions about that, we can talk about it. But both of these complexes operate, they control Z selectivity by what's called a side-bound or side-on ruthenocyclobutane mechanism. The simplified cartoon drawing of that I'll show here, which is you have the MES group, and that this has been elaborated further based on this hypothesis. You can make even bulkier, but the ones here are the MES. So if you make a dip, the catalyst is even more selective. And the other ligand environment around here, I'm just going to draw in kind of like cartoon form. They force the cyclobutane to be, it can be bound side on or bottom on. And so it forces it to be side on. And the result of that is that these groups have to go down. And this was elucidated by collaboration with the Haupt lab.
Can I ask a clarifying question?
Sure.
In the CMD step.
Yeah.
Sorry, it's a silly question, but where's the proton that you have extractors go to?
So okay, let me walk you through this. So if we imagine, if we draw your eye to this intermediate here, after the salt metathesis step, we make this kind of intermediate.
Oh, yeah.
And then upon CMD, you will lose one equivalent of
Oh, I see. Okay.
fib OH.
Okay, sorry.
Yes, is that clear?
Yeah.
Okay, it's a good question. Okay. All right, let's talk about chemoselectivity trends. So this graph is just reproduced from this accounts paper from the Grubbs lab. I really like it because it solves everything out clearly. It just situates the relative reactivity of olefins compared to other functional group, normally protic or oxygen-based functional groups, encountered in synthesis. And shows how this order of reactivity changes as a function of the metal. And now how can we rationalize that? Again, we always try to bring things back to first principle. Let's zoom in on the electronegativity values of the metal. And sure enough, the more covalent we get in that metal carbene bonding, as we approach the electronegativity values of carbon, we get better chemoselectivity for olefins compared to much more polar functional groups. So the less polarized the metal, the more chemoselective it is for olefins. And the other point here is that the ruthenium catalyst, if we compare the molybdenum catalyst and the ruthenium catalyst, both are really useful in their own right. The molybdenum, they will always win out in terms of reactivity. Turnover number, turnover frequency, those are the ones to pick, molybdenum or tungsten-based ones. And so why are the ruthenium ones, had they gained so much traction over the years? It's because of their chemoselectivity. It's exactly what's depicted here, is that they can operate unlike some of the other ones, although I will say that there have been really nice advances in the past couple of years about more functional group tolerant tungsten and molybdenum-based catalysts. In general, the ruthenium ones people use, even though they might only undergo 100 turnovers, because they have such pronounced chemoselectivity and can tolerate air and moisture, et cetera. Okay. We're kind of getting near the end, got 15 minutes left, so we'll wrap things up here with taking a look at these two problems of the day and then quick discussion of cross metathesis selectivity rule. So let's consider these two problems of the day. I'll flash them up. Sorry that I thought we could get this fixed, the screen issue fixed. So sorry that didn't, probably knowing our luck, they'll come like as soon as the class finishes. Okay, so problem of the day is number 2 and 3 here. And first, to orient everybody, both of these are not catalytic per se. These are stoichiometric reactions. So problem of the day number 2 asks you to consider a collection of olefins in this reaction that we're running under pseudo first order conditions. And it's really intended to probe your knowledge, your intuition of relative reactivities of these different olefin substitution patterns in a single step, not in a catalytic turnover, which then I think convolutes things, but just in this initial 2+2 retro 2+2 sequence to go from one well-defined complex to another well-defined complex. Problem number 3 is a treatment of this alkenyl ketone starting material with Schrock type initiator and asks you to consider the first do an electron count of that starting material, starting complex, and then predict the products and mechanisms. All right, what do we think here? David, what do you think here for relative reactivity? What's going to be the most reactive?
You zoom in.
Which one?
You zoom in.
Let's see, I can zoom in. Do it. All right, A, B, C, D, or E. What do you think will be most reactive?
C.
D. Why do you think C?
Inductive effect of the blue marker group.
Okay, so you're invoking electronics and the level of electron richness. But what do we know about these catalysts? From that example I showed from Jan Schia's group, we know that sterics play an important role. So if I told you to orient your thinking along, at least initially along steric lines, what would you think?
A.
A, okay? That's a good place to start. I think that's kind of a common theme across organometallic catalysis, many different mechanisms. You know, terminal alpha olefin is normally a good place to start in terms of relative reactivity. Okay, and then what do we think next? Now there's kind of no easy choice. Everyone has something wrong with it from a steric perspective. So what would you if you just have an intuition, gut's
B,
leading you one way, what, D?
D, then C, and
B then C, D then E. Okay, so I think that is reasonable, but that's a reasonable way to think about it. But I will say that and when we look at the mechanism, we can talk about why this is the case. But these one disubstitute olefins and these hindered allylic disubstitute olefins are quite slow, whereas internal ones are a little better tolerated. So I think your thinking is on point here. So if I told you internal is the next most reactive, then do you like Z or E on steric grounds?
so I'll take D.
D, okay. D, E. And then I think this, you know, if you don't have a strong intuition, B or C is, I think that's fine. If you don't, you have to guess. But C turns out to be very, very unreactive. These quaternary substituted ones, they're just very hindered. So if anyone wants to read more, here's an organometallics reference. I will say that this reference you can look at for this rate data. It does have the mechanism a little bit muddled, so don't rely on that as primary literature for thinking about the mechanism. There are more up-to-date references than that, but just for the rate data, we can look at that. All right, how about problem of the day number 3? What do we think there? Clara?
So when it's like 0 to D6,
Cool it down. Want to shift the screen.
Yeah, thanks. Maybe I'll go to share my drawing pad. Actually, maybe I'll zoom in here because I don't have the whole structure drawn out. All right, so the first things first, we got to make some choices. So we've got this amido and it's drawn linear. So it's drawn in implicitly with the lone pair. So nitrogen is sp hybridized. So the lone pair is implicitly playing a role in bonding. And then we've got to make a call about whether this is a Fischer or Schrock type carbene for our electron counting. So those are some of the first issues we need to confront. So how about, give me your thoughts, Fischer type carbene, Schrock type carbene, what do you like here?
Schrock.
Drop, why?
Just because there's like, it's not as electron withdrawing.
It's a relatively early transition metal in a relatively high oxidation state. So looks good for Schrock. And then, so we're gonna count that as a X2 ligand. And then we've got this terminal amido. How are we gonna count that?
L maybe? I'm not entirely sure.
Okay,
Or
it-
S, or maybe X.
well, if you, like, first things first, if we were to just dissociate that ligand to a closed shell species, how many minus charge would it have?
So I guess 2.
It would have 2, great. So it'd be bis anionic. So that gives us a hint that it's gonna be at least X2, but maybe more than X2. So X2 plus we talked about the lone pair implicitly
It's 2L.
X2L. Okay, great. All right, so then we're halfway there. We've done all the hard work, actually. We're more than halfway there. So just take us home here.
Okay, and then each of the ORs is gonna be X.
All right, so overall, what do we have? We've got molybdenum is what oxidation state?
So you know, it's +4. Or
Alkoxy, Schrock carbene, and then amida. So that will be +6.
oh yeah.
Okay, all right. +6, which makes D what?
So it's D0.
0. And then what about the rest of the electron counting? Now we've got 1, 2, 3, 4, 5, 6,
So
7.
yeah, so 14.
Overall electron count 14. So that gives us an idea. It's going to be pretty kinetically reactive in all likelihood. And I think one of the points I'll just highlight here is, even if you don't get that amido part, and that's a little tricky, the linear amido, you can get 99% of the problem right. And then if you got there and you're like 12 electrons, that seems like it would be super reactive. Should I double check my work and like, oh, okay, linear amido, that might help there. Okay. How about awesome job, Clara. So now reactivity, what do we think there? Mike, what do you think?
I would think it could just do normal cross metathesis, like the oxygen atoms, I would think are a problem for molybdenum.
Okay.
So I guess first guess is just normal metathesis, otherwise it forms a chelate with the.
Love it. So we can just go to our handy dandy chart and the molybdenum section and say, what are we dealing with here? We've got a ketone and we've got olefin, and there's similar reactivity, but actually the olefin wins out. So we're going to do that first, which is exactly what Mike said. Oops. I don't know if I can, let me see if I can. Oh, okay, all right. So I don't want to, I already showed you this. So we do that once, and then you stick the molybdenum on the terminus of the olefin, and then what? Spins around?
You showed it.
Yeah, okay.
But it does ring closing, I guess, but is that kind of like almost like a Wittig though?
Yeah, I think that's a reasonable way to think about it. You've got an alkylidine that's relatively oxophilic, tethered intramolecularly, so it can undergo 2+2 retro 2+2, but now it's doing that with a carbonyl. It's spitting out a metal oxo. So this is an example of a intramolecular carbonyl olefin metathesis. But what do we expect? Let's take a look again at the reaction conditions from the problem of the day worksheet. We have to use one equivalent. And why is that?
Can't turn it over.
Can't turn it over. You generate the molybdenum oxide. That's what gives you that strong thermodynamic driving force. But just like a Wittig reaction, you made that analogy to a Wittig, which I think is very insightful. You need that thermodynamic driving force to do the transformation, but once you in that thermodynamic well, you're in the well and you can't regenerate the catalyst. And this is actually, there's a lot of interesting organometallic reagents that mediate carbonyl olefin metathesis. Most of them cannot be turned over catalytically for this exact reason, and this is why this topic has endured as a research area for many decades. Actually, ironically, despite this paper using a Schrock type initiator, this was a report from the Grubbs group with Greg Fu as the first author during his postdoc. Okay, we'll wrap things up here with just couple minutes of notes on cross metathesis selectivity rules. And if you get nothing else out of this part of the lecture, I just want to draw your attention to this key leading reference from the early 2000s. The first author on this, there's a Scripps connection. This is none other than our very own Arnab Chatterjee, who now works at Calibre. He did his PhD with Grubbs. At Calibre, he's, of course, risen to fame for this reframe drug repurposing library, but prior to being a distinguished medicinal chemist, he cut his teeth as an organometallic chemist. The point of this paper was to provide a user's guide, so to speak, for as a function of the catalyst used, how the olefins with different substitution patterns react. And so it's organized into 4 different types: those that undergo rapid homodimerization, those that undergo slow homodimerization, those that do not homodimerize at all, and those that are effectively inert to cross metathesis. And if we consider the case of the Grubbs 2 catalyst, of course, you can consider other catalysts and which olefins fall into which type changing. But if we consider the Grubbs 2 catalyst, and if you're curious about this, this will be in the handout for the class, so direct your attention there. If we consider the Grubbs 2 catalyst, the types, choosing the appropriate type allows us to get selectivity that is beyond what you'd expect from statistical selectivity. So if you mix 2 type 1 olefins, all you can hope for is statistical selectivity in a cross metathesis. And let's say let's play this out. You need a given target molecule in the context of a synthetic endeavor, and one of your coupling partners is cheap, one of your coupling partners is valuable. Often the way that you would try to push this then is bias it by putting statistics on your side, by using 10 equivalents of one coupling partner and the other as a limiting reagent. Similar logic for mixing type 2 and type 2, or type 3 and type 3. But where you can get selectivity beyond statistics is mixing type 1 with type 2 or type 3, because in effect, what this allows is every step of the catalytic cycle to be precisely choreographed. So the olefin that you want is coming in only when you want it to come in. So this is where I'll wrap things up, the prevailing mechanism. And this was outlined actually by none other than Melanie Sanford when she was a graduate student in the Grubbs group. That's, I think, what first brought her to national and international notoriety, is this seminal series of mechanistic studies. Some of the key features here are that with the ruthenium initiators, there needs to be an initial ligand dissociation step. So you start with a 16 electron complex, you initiate by losing an electron to get, losing a ligand to get to the reactive 14 electron version. Coordinate your olefin, and now it's the Chauvin 2+2, retro 2+2 sequence. And I think this gives you a sense, I was asking David about the relative reactivities of olefins. I think this allows you to get a sense for why some olefins are slow to react. For example, if you imagine this R1 olefin as instead being doubly substituted, boy, you start to get a lot of steric hindrance proximal to the olefin or to the metal, which is large on the metallocyclobutane structure. So that's the origin of the steric selectivity. Is every olefin that you bring in, those substituents eventually need to be splayed about this highly congested metallocyclobutane. So it has really profound steric sensitivity as a function of its reaction mechanism. So I'll leave things there. Reminder that there's no class on Thursday for anybody who walked in late, as since we'll be observing Juneteenth, and then we're back in action on Tuesday with a guest lecture from Jin Kwan. All right, thanks everybody.